We're going to start a new unit that's called electrochemistry. And electrochemistry is the branch of chemistry that studies the interconversion of electric energy into chemical energy and vice versa. And we will start by refreshing some concepts that you have to learn in first semester chemistry when you were about chapter, I believe it's chapter 3, reaction in aqueous solution, and one of the three main categories you have studied precipitation reaction, you have studied acid-base reaction, and then there were oxidation reduction. So we're going over those concepts that you may not remember, right? So let's start by talking about the very basic definition. What are oxidation reduction reactions? There's a lot of alliteration there, so we normally just shorten it up into redox. So we are talking about two reactions that always happen at the same time. So whenever you have an oxidation, you also have a reduction. And whenever you have a reduction, you also have an oxidation. And this is because electrons, they have their own mass, so its mass is matter, and we know that there is a low conservation of matter. Therefore, we cannot have disappearance of electrons or electrons coming out of nowhere. So we need to account for those electrons. So whenever there is a species that's losing electron, the implication is that there has to be another species who's taking those electrons in. And also the implication is that when we balance oxidation reduction reactions, we need not just to balance the atoms, but also the electrons. So when you have a reaction that's probably balanced and there are species that has charges, you should be able to put together all the charges left and right of the arrow, and you should see the same total number. If the number of the charges is not the same, there's something wrong with the balancing process. So one of the examples you've seen most often in the lab, you actually did this experiment in Janken 1, was to mix zinc with a solution of copper ions. So zinc was metallic. In the picture here you see a bar of zinc, but in your experiment you had what we call mossy zinc. So it was like little irregular shade, but quite smooth chunks of zinc. And what you saw was that, so the solution of copper ions was blue. You now know about complex ions and why transition metals complex ions are colored. So the reason is blue is actually that there is an aqua complex where copper is bonded to water, right? But what you would see is that some of you were more patient and would wait a little bit longer and could see the full evolution of the reaction. The zinc was becoming initially darker, black, covered in tarnish, let's say oxide on the surface, and then it would disintegrate, and you're forming zinc ions. Zinc ions really don't have any color for reasons that we have seen when we're talking about complex ions. So they don't change the color of the solution per se, but what happens is that copper ions are used up, so the blue of the solution is fading over time, and you would see that the deposition of some that you can kind of see in this picture also is very around here. There's some reddish material that's metallic copper. Sometimes you in Janken 1 you may say, oh, I think there's rust forming. That's not rust, that's copper, but the color is deceiving. And eventually you would see more and more copper forming, and the solution would consequently fade. Eventually you may even see that the solution loses the color completely. So if we would have a magical microscope that we could see the atoms, we would see that for the reaction to happen, there has to be a direct contact between the copper ions and the zinc, the metallic zinc, for the electron to be transferred. So the reaction consisted to a transfer of electrons from zinc that's losing them to copper. However, electrons do not dissolve in water, they don't travel in water, so in order for the transfer to happen, there has to be a physical contact. Why is copper stealing electrons from the zinc? The two metals have a different affinity for those electrons. So if we could rank those two and say that the copper is stronger in its affinity for electrons, is able to steal them from zinc. So copper is becoming neutral and therefore becoming a solid, so it's depositing on top of the zinc, so it's a sort of an electroplating situation, while zinc is being now deprived of those electrons, is an ion, and is now soluble and colorless and going into the solution. Now, as it happens, copper to become neutral needs 2 electrons. That's exactly the number of electrons that zinc is giving away. So the reaction ratio is a 1-to-1 ratio. Now, if you would manage to force those electrons that are transferred spontaneously, we are doing nothing, the reaction happens without our intervention. If we were able to force those electrons to go through a wire instead of transferring directly, we could use that to produce electricity and maybe turn a light bulb on. And so, but we need to use some ingenuity, and because electrons are, I used to say in class, they're a bit like students, they're a bit lazy, like every human being actually, including teachers. So if there are 2 ways to accomplish something, and one is easy and one is hard, we always take the easier route, right? So this is the easier route for the electrons. To get them to go through a wire would be the difficult path, the most difficult path. So we need to kind of force them to do that. That wouldn't be their spontaneous choice of path. So let's see what happens in terms of reaction. We can split the oxidation reduction into 2 halves that are called half reaction. So we can study separately the oxidation and the reduction. And this makes easier the process of balancing, that now you would think is pretty easy as it is. You could balance this reaction even without knowing it's an oxidation reduction. But that's because it's an easy one. And balancing oxidation reduction could become quite a challenge. We are really not going into that, but in which case you really need to keep track of all your electrons. So from the perspective of zinc, what's happening is that zinc goes from neutral, solid, metallic, so a nice shiny gray bar, to a colorless soluble ion, and in the process is losing 2 electrons, so the electrons are written on the product side. Copper, on the opposite way, does the opposite thing. Copper ions that are, blue in coloration. It's more when they're bonded with water, but we don't need to complicate that too much. Copper ions are acquiring 2 electrons, forming solid copper, metallic copper, so with the typical orange coloration. So the first reaction is the oxidation. Zinc is oxidized, and that would be what in plain English we would normally say it's tarnished, it's rusting, if it's iron. Copper, vice versa, is reduced. So zinc, because it's oxidized, is causing the reduction of copper. Copper is reduced because of the presence of zinc. So the zinc is the reducing agent, but zinc itself is oxidized. So that gets a little bit confusing in terms of wording sometimes. Consequently, copper is the oxidizing agent because it is the reason why zinc gets oxidized. So it's like one is the victim because the other one is the culprit. To remember, there are different ways you can use. How do you know which one is oxidized and which one is reduced? So if you notice zinc, that's the one oxidized, its oxidation number is going up. If you don't remember what the oxidation numbers, we are going to go to refresh it right away. But basically the charge is going from 0 to +2, so it's getting bigger. As opposed to copper, when it's going from +2 to 0, so it's getting smaller. It's getting reduced. Another way to, and also you need to remember that sort of switch of, the reducer is oxidized and the oxidant, the oxidizer is reduced. Another way to remember it that I think is the most useful is the so-called oil rig mnemonic. So the letters that are colored, O and L and R and G, are for oxidation, loss of electron, and reduction, gain of electrons. How do you know if a reaction is a redox? So if you get a question where you have 3-4 reactions and they are asking you to identify which one are redox and which are not, so you need to find at least one element in the you need to use the oxidation numbers. You want to calculate the oxidation numbers, and if there is at least one element for which the oxidation number is changing, then that's a redox, because if that one is getting either oxidized or reduced without even checking, you know for a fact that there is someone else that's getting oxidized or reduced. Now, acid-base reactions are never redox and vice versa, so that's kind of a shortcut. Combustion are always oxidation. It's kind of the poster child of oxidation. Combination from the elements, direct combination from the elements is an oxidation reduction, because the elements, by definition, they have oxidation number 0, and they end up in a compound where they have some oxidation number that's not going to be 0, so that's a redox as well. So there are some ways you can kind of figure it out without actually having to do the math, but calculating the oxidation number would be the safest route. So let's talk about this oxidation number. Sometimes there tends to be a certain confusion between oxidation numbers and formal charges. So maybe if we see them side by side, we can understand what's different and what's similar. So let's use a very simple molecule, like a molecule of water. In your first semester chemistry, you will learn that in a molecule of water there are two covalent bonds between hydrogen and oxygen. And those are covalent polar bond, because there is a difference in electronegativity between oxygen and hydrogen. So the two electrons that are used to make each bond are shared, but the sharing is not even. Oxygen tends to attract those electrons more strongly than hydrogen does. So there is an excess of negativity on the oxygen, there is an excess of positivity on the hydrogen. That's why molecules of water are overall polar, due to the presence of a polar bond and the fact that the molecule is not symmetrical, right? So it's not the one between oxygen and hydrogen is not an ionic bond, because in an ionic bond there would be a complete transfer of electrons between one atom and the other, and you would have ions, you would have full charges. Is not a covalent non-polar bond, because that would happen between two atoms that are identical, like two atoms of hydrogen in H2 or two atoms of oxygen in O2, in which case the electrons of the bond would be shared perfectly even. It's somehow kind of, let's say, a middle ground between an ionic bond and a non-polar covalent bond. Okay, when we are calculating the oxidation number, we are sort of doing a pretending job of, we are pretending that all the bonds are ionic even when they are not ionic. So for example, in this case, so of course, if you're calculating the oxidation number of NaCl, that's ionic, no big deal. The oxidation number corresponds to the charges on the ion, but you can calculate the oxidation numbers even in for molecules in which there are no ions, right? So we need to pretend that the bonds were ionic. What would happen if the bonds were ionic? How would that happen? The bond between hydrogen and oxygen would break, and the two electrons that are involved in the bond would go towards the most electronegative. That would be oxygen. So oxygen would get 2 electrons on the right, and 2 electrons on the left. So getting a total of 8 electrons. Now normally oxygen has only 6, right? So it would have 2 negative charges. While hydrogen would be left completely naked without electrons, so it would have a positive charges. That would be the same on the other hydrogen. So that would be the oxidation number for oxygen, plus 2. It's not the actual charge that you have on oxygen, because it's not water is not made of ions. You do have a little excess, but this is much, much less than the 2 full charges that you are seeing depicted here. So this is not reality, it's just a figment of imagination, but allows us to assign a number that's called oxidation number. This is very useful when we're doing balancing of redox reaction. So the oxidation numbers would be -2 for the oxygen, -1 for the hydrogen, and when you put them all together, you get the same charge that you have on the molecule as a whole. This is a neutral molecule, so the overall charge of the molecule is 0, and in fact, -1 minus 1 is +2 is giving you 0. Okay, so that's how we calculate oxidation number, pretending everything is ionic, even for those molecules in which there is no ionic bond. What about formal charges? It's kind of the specular thing, the mirror thing. We pretend that all the bonds are covalent, non-polar, in which case, when we break the bonds, the bonds would break exactly in the middle, and the electrons would go half one way and half the other way. So what I do when I calculate formal charges, I use this method that I call the bubble method, because I draw a bubble so that the bubble cuts in half all the bonds. And then you count what's inside the bubble. In this case, I draw the bubbles only for oxygen, but you could draw 2 little bubbles for the 2 hydrogen as well. So then you count how many electrons you have inside each bubble. So for the oxygen, you would end up with 6, because you have the 2 lone pair that you had to start from, and then 1 bond per each, 1 electron per each bond that's been broken, so it's 6. For hydrogen, you would have 1 and 1. Now, what does this tell us? We need to compare this number of basically the number of dots around each atom with the valence electron. So how many valence electron has oxygen? 6. 6 is the number of the electrons that he has, let's say, is his starting ground. After we did this bubble, how many electrons does oxygen have? 6. So he has exactly the same number of electrons that would be its valence electrons. That means that it has not acquired or lost electron. That means its formal charge is 0. Same for hydrogen. 1 electron should have, 1 electron has after this breaking, so the formal charge on a hydrogen is 0. Once again, the sum of all the formal charges should give us the sum of the charge on the molecule as a whole. In this case, this molecule is neutral, and so 0 plus 0 give us 0. There are some simple rules to determine oxidation number that you have probably learned in your first semester of chemistry. First of all, elements in their uncombined state, so in their elemental state, would have an oxidation number of 0. So like sodium, metals like sodium, potassium, also biatomic molecules. Let me get the last point. So for example, you see IH2 is not a monatomic molecule. There are 2 atoms, but because the bonds in between 2 identical atoms, the oxidation number stays 0. Same if you have more complicated elements that would form larger molecules in their elemental state, like phosphorus or sulfur. So for all the situation is 0. To remember, there's a way to remember all the molecules that have a biatomic formula, and this is have no fear of ice cold beer. Then if you have an ion that's made of just 1 atom, monatomic ion, so for example sodium plus, iron plus 2, aluminum plus 3, sulfur minus 2, fluoride minus 1, and so forth, the oxidation number is the charge on the ion. There is no figment of imagination there, they're already ions. Then there are some trends. Oxygen typically is -2. The only remarkable exception are peroxide, of which the most likely that you may encounter is hydrogen peroxide, in which case is -1, because in hydrogen peroxide there is a bond, one of the bonds that oxygen is making is in between 2 atoms of oxygen. So bonds between identical atoms do not count in terms of oxidation number. So unless it's a peroxide, in which is -1, you can kind of make a safe bet that the oxidation number of oxygen is -2. Same for hydrogen. The vast majority of the time, hydrogen oxidation number is +1, like we saw for water. The only exception is where it is bonded to metals, for example, in which case it's -1. In group 1, where you have sodium, potassium, lithium, and so forth, for the same reason why they form cations with one charge, their oxidation number is +1. Same for group 2, where they would form cations with 2 positive charges, therefore their oxidation number is +2. In groups 17, so the halogen, the only one that you can safely bet on is fluorine, -1. For chlorine, iodine, the things are more complicated because they have compounds in which they bond with oxygen, in which they end up having oxidation numbers that are positive. But fluorine, being the most electronegative of all the elements, is only -1 is an oxidation number. Then a useful thing is that, as we've seen for water, if you sum up all the oxidation numbers in a molecule, that number is identical to the charge of the molecule as a whole. So if the molecule is neutral, the sum of all the oxidation numbers should give you 0. And so this is useful when you are asked to calculate oxidation number, because some elements are predictable, some other elements, they can have so many different oxidation numbers that you can't, it's hard to tell. So for example, if you want to know what's the oxidation numbers of each of the element in HCO3, so bicarbonate ion, you can use the pattern, a couple of the rules. For hydrogen, is not bonded to a metal, so it's +1. For oxygen, is not a peroxide, so it's -2. Carbon is all over the place in terms of oxidation numbers, but because you have only one unknown, and you know that the molecule as a whole is charged -1, so you know that the sum of all the oxidation numbers, so +1 for hydrogen, and then 3 times -2 for oxygen, and then plus X, that would be carbon, should give you -1, right? So you can basically you can do it in your head, or you can use algebra, and you will figure out that carbon is +4. Carbon pretty much can have any number between +4 and -4. So here we can do some practice, and what I want you to calculate is the oxidation of nitrogen, number of nitrogen, the oxidation number for chromium, these two nitrogen here, and it's kind of interesting to compare them to each other, and these two sulfur here, compare them to each other, and these two carbons. So push the pause button and then come back and we can see the results. So these are the oxidation number for these compounds. So the first two, let's say the thing that could be tricky is that you for example, you take the oxygen here, and let me get the pointer. You take the oxygen here, so it's the one where you can predict the pattern. So oxygen is always -2. This is not a peroxide, so it's -2. So -2 times 4 is -8, and then that -8, the total should be 0 because the molecule is neutral. That -8 needs to be spread over 2 nitrogen, so you need to divide by 2, and you get 4. Same kind of situation here. Here you have nitrogen bonded to different amounts of oxygen. So you have nitrate, a nitrite, and a nitrate. And you know why chemists prefer nitrates? Because they are cheaper than dirates. So in this case, there is less oxygen, the oxidation number is +3. Here you have more oxygen, the oxidation number is +5. So that's kind of an interesting pattern to notice. For sulfur, this one was a tricky one. It's seems like a complicated molecule, but all the bonds are between sulfur and other sulfur, so it's sulfur in its elemental state, so the oxidation number is 0. Here you need to keep in mind that the sum of all the oxidation numbers should give you -1, because there is a -1 on the molecule, so it's +1 plus X plus 3 times -2 equals -1, and then you solve per X. And these two are interesting, is hydrocarbon, methane, and carbon dioxide, -4 and +4. These are kind of the two extreme oxidation numbers that you can find for carbon. So you can get those two numbers and any numbers in between those. So it's kind of an interesting pattern, because the more oxygen the higher is the oxidation number. And between oxygen and hydrogen, a lot of oxygen means a high oxidation number, like in CO2, and a lot of hydrogen means a lower oxidation number, that is -4. So whenever you have carbon compounds and you're adding hydrogen, that's called a reduction. And CO2, having carbon the highest possible value of oxidation number, cannot burn any further. So that's the maximum oxidation, so the maximum combustion that you can get. So this is a periodic table where you see the different oxidation numbers for a lot of compounds. Not that anyone has the expectation that you remember that, but what I want you to pay attention to is the fact that so here you see hydrogen +1 and -1. -1 would be when it's connected to something that is less electronegative than it is, so it would have to be connected mostly with metals or with boron. The oxidation number correspond to the charge on the ions. Here you see the fluorine is the simplest behavior, that's -1, but chlorine could have all these positive values, and that happens when it's connected to oxygen, because oxygen is a bit more electronegative. You see that there are no oxidation numbers for noble gases because they don't form any compound. Krypton and xenon can form some compounds. That was really hard, and I believe that the scientists who managed to do that won the Nobel Prize for chemistry. The other interesting behavior is the transition metals, where you already know that they can make different type of ions. They can also have many different type of oxidation numbers. So look at manganese, it's really all over the place. Sulfur too is another one that has quite a variety of oxidation numbers. So let's go back to our experiment with the copper and zinc, right? So you have your copper. Here you also have, it may look like it's just a shade, but that's actually a bar of zinc. So you see that after a while you have used up all the copper ions. The solution has become colorless, and now you see copper deposition in the test tube. So the reaction that's happening, it's summarized at the bottom part of the slide, with where I also try to give you a sense of the colors of what you see, right? So the thing is, this reaction tends to happen one way only. So if I try the opposite, I put a bar of copper in a solution of zinc, nothing happens. And so there is definitely a ranking between those two elements, like where copper ions are very effective in stealing electrons to zinc, while zinc ions are not effective at all in stealing electrons to copper. So there is a very strict directionality. One of the two is spontaneous, the other one is not. So we have kind of just finished thermodynamics, so it's going to be interesting to connect these two units and figure out how to predict the spontaneity of oxidation. We have our spontaneous reaction between zinc and copper ions that consists into the transfer of electrons from zinc to copper, and we would like to exploit this to produce electricity, but we are unable because the electrons are following the path of lower resistance, going directly from the metallic zinc to the copper ions, and instead we would like them to go through an external copper wire. So we need to separate those two solutions, but then if we separate them, we have another problem. Okay, so let's consider what's going to happen. On this side we have the bar of zinc, and the bar of zinc has been connected with a metallic wire to a bar of copper on the other side. So these two metallic components of the setup are called electrodes. The zinc is going to get oxidized according to the reaction that's written down here. So the zinc is going to lose 2 electrons. Therefore, this electrode is rich in electrons, is the negative one. The electrons are going to go not having a direct connection with the copper, they have to reach to the copper side. They need to go through the wire, do the work that we want them to do, that is to light up the light bulb, and then finally they can arrive here where they are attracted by the copper. So this is the positive pole that's attracting the electrons. And here they can connect to they can be transferred to copper ions and form copper. So you would see some copper depositing on top of the electrode. And this electron is getting chubbier and chubbier. Conversely, this electron is getting smaller and smaller because the zinc is used up in this reaction. There's a problem though. As the zinc is going to be oxidized, right, because this is what's happening here, is the oxidation of zinc, you're going to form this positive zinc ion, so the solution is getting more and more rich of positive charges. Conversely, on this side, you're going to have an accumulation of negative charges because copper is used up, so it's disappearing from here and is becoming metallic copper that's neutral. Now, this copper must have been associated with some counterbalancing ion. I cannot go to the stockroom and say, hey, give me a bottle of positive ions. They always come as salts, right? So this could have been copper sulfate, copper nitrate. Let's say it was copper nitrate. If the copper is going to become metallic, all those nitrate ions are going to be unpaired, left in the solution. The solution is getting more and more negative. If this is getting negative, is reducing the ability of the electrons to come, because they don't want to come to a solution where that's already negative. There would be repulsion. While on this side, the electrons will have a hard time leaving this side if it's positive and is attracted them. So the reaction would stop. Right? So we need to assure an electrical continuity between these two solutions. And this is obtained by means of a salt bridge. The salt bridge is a conductor that allows the two solutions to be connected so that the circuit is closed. When a circuit is closed, you can have electricity flowing through it. If the circuit is open, it's like when your lamp on your desk has the switch in the open position, the light bulb is off because the circuit is not closed. But also, in the salt bridge, you have gelatinous, something that looks like jello is a gelatinous solution made out of agar, for example. That's an algae. And it's very rich in ions, so there is a lot of, for example, potassium ions and nitrate ions. Why do we pick potassium and nitrate? Because they have nothing to do with the reaction, so they are spectator ions, right? So as this is becoming negative, the potassium ions will flow inside the salt bridge into this side of the solution, while the nitrate ion will flow into the salt bridge and go to this side of the solution to keep it neutral. So there's going to be a flux of ions from the salt bridge to the solution that will let the solution to be neutral. So in order to understand electrochemical cells, we need to get familiar with terminology of electrical circuits. We can see electrons, so it's sometimes hard to understand what's going on because it's quite abstract. So let's use an analogy with something that we may be more familiar with. That would be water being moved in a circuit. For example, let's say you have an aquarium, a fish tank, right? So and the water is kept in constant motion through a pump. So the pump is what provides the energy. What provides the energy to keep the water moving, is the driving force for the water to move. That would be the electrical battery. The electrical battery has a positive and a negative side. The current traditionally is described as going from the positive to the negative, because when they discovered electric current, they knew nothing about electrons, and we have in bias for positive versus negative, so it came natural to them to assume that whatever was moving was the positive one, and then they ended up discovering afterwards that it was the negative, but it was too late to change the standard. So in an electrical circuit, the current goes from positive to negative, but what's moving are the electrons. The electrons are going from negative to positive because they are negative, they are attracted from the positive side. So there is a bit of an inconsistency there. So in your aquarium, you may have that at some point one of the pipes there's stuff stuck in it, right? So that would cause the pressure to drop, and would decrease the rate of water that's coming out from the other side. So that would be the same as electric current going through a resistance. So you see here a typical way that electrical circuit is represented. So you have the wires, and then if you have a resistance, it's not represented here, but it would be represented as a zigzag type of thing. You have, let me go back to the pointer. This would be whatever is using up the electricity, so it's an utilizer, and it would have a resistance in itself. The battery is represented by two lines. The shorter is the negative side and the longer is the positive side, and then you have the switch. That's like the switch in your lamp. What's slightly counterintuitive is that when the switch is open, when the circuit is open, there is no current going through. When the switch is closed, that's when you can have the current flowing. That's the opposite of a door. When the door is closed, you can't go through. When the door is open, that's when you can go through. So it gets a bit confusing. So this is a bit of a summary of the units. Anything that would be relevant to solve problems would be provided in the cover of the exam, so you don't have to worry to memorize it. So I would like to conclude this PowerPoint with an historical note, right? So the volts, they take the name from Alessandro Volta. That was the scientist who is believed to be the first one who put together a battery by alternating discs of zinc and copper. And another Italian scientist, Galvani, made some experiment using Volta's device and frogs, and frogs are quite a delicacy in the part of Italy where Galvani and myself are coming from. So he probably had easy access to these frog legs. Now, obviously, the frog is dead, and what was really amazing for the amazing things he did he would take these dead legs and apply electricity to it and manage to get them to move. So, and this was extremely an extremely powerful result for the people of the time, because it was a dead body to which some sort of elementary form of life was given back by something human-made. So, and this is the inspiration behind the story that came afterwards, written by this lady. And you may not recognize the lady, but you for sure will recognize her fictional character, that it was in fact kind of similar to the frog. It was a bunch of parts from different corpses and, you know, stitched together, and then it was given back life through application of lightning. So that's, you know, where the story is coming from.